So what you want to do when you're solving these problems is do the following shortcut, okay? So for each symmetry operation, first, determine the number of stationary atoms. The reason why you want to do this, right, is because the stationary atoms are the only atoms where you will have a non-zero value on the along the main diagonal of the transformation matrix. So we're going to call that gamma stationary, a representation that has to do with the stationary atoms for each symmetry element. Then you're going to determine how X, Y, and Z transform, because after all, that's what you care about, right, for each of these atoms. So we'll call that gamma X, Y, Z. And then to find the total transformation representation for all the degrees of freedom, I'm calling this gamma nuclear, you just multiply the two. All right, so let's show you how this is done. And this ends up saving a lot of time because you're only solving for things that you actually need in your end result, right? So here again, we have water, and we're trying to figure out the normal modes for water. So we can draw our Cartesian coordinate system on each of the atoms. And again, we're trying to find out gamma nuclear by figuring out gamma stationary and gamma XYZ. So gamma XYZ, we ask the question, okay, what happens to XYZ? Well, if we do, and that's going to be on the center of the molecule, okay? So that's always going to be on the center of the molecule. So in this case, that's oxygen. What happens to X, Y, and Z when you do the identity? Well, X is going to go into X, Y goes to Y, Z goes to Z because the identity doesn't do anything. And so you'll have an identity matrix, right? One's across the diagonal. Now I'm not explicitly showing the matrix, but remember, we're always, that's what we're doing. We're always evaluating the character of the transformation matrix. In this case, it's for X, Y, Z. And so it's going to be 1 plus 1 plus 1 equals 3. So that's going to be your first value for gamma XYZ. You go along here and you do it for C2. C2 is 180-degree rotation, right, through the Z axis, through the oxygen, the central atom. And X is going to go to minus X, right, because you're doing 180 degrees. Y goes to minus Y, and Z stays unchanged. That gives you a matrix with -1, -1, and 1 across the diagonal. Add those up, you get -1. That's your character there. Keep going, go to XZ. XZ, that's a mirror plane like this if your molecule's here, right? It's a plane right in here, okay? And so any vector that's in the XZ plane is not going to change. So X goes to X, Z goes to Z. But Y is on one side of that mirror plane, so it's going to flip to the other side. Y goes to minus Y. So you have 1 plus -1 plus 1 gives you 1. Lastly, we do the YZ plane, and this is going to give you the same answer. It's just you had a -1 for X now and a +1 for Y because Y is in the mirror plane now. And that is how you figure out gamma XYZ. So our reducible representation for XYZ is 3, -1, 1, and 1. Now we do gamma stationary. Gamma stationary is even easier. Gamma stationary, what do? You just ask for each symmetry element how many atoms stay the same. And so when you do identity, all the atoms are going to stay the same. So that's going to give you 3. When you do the C2, right? Well, how many stay the same? Only the oxygen. The hydrogens change places, and so that's going to be a 1. XZ, that's splitting the water molecule in half. The hydrogens change places. The oxygen stays the same, so that gets a 1. And YZ is in the plane of the water molecule. So all of those atoms, both hydrogens and the oxygen, are not going to move. It's a planar molecule, and YZ is defined as being in the plane of the molecule. And then you multiply them together to figure out gamma nuclear. So you're going to get 9, -1, 1, and 3. 3 times 3 is 9, etc. Now, at this point, you got to go to the character table, and we need to reduce this representation, right? This is What is gamma nuclear? It is a combination of irreducible representations, right? It's a reducible representation in C2V that describes the symmetry of all the different degrees of freedom that these molecules have that are orthonormal to one another. So it's setting up the conditions for describing basically all the different ways that these atoms can move that is compatible with the symmetry of the molecule. And in order to get out the normal modes, we're going to have to reduce this reducible representation and then subtract off the translational and rotational modes. So we go ahead and use our reducible representation formula. If you're not feeling too confident on that, please go back to the chapter 2 slides. But this is going to decompose into 3A1, 1A2, 2B2, 2B1, and 3B2. And remember, again, going back to chapter 2 stuff, that you can always check your answer here, right? So if you go 3 times A1, you're going to get 3, 3, 3, 3, and then add in 1A2 and 2B1s and 3B2s, you should get back a vector, a 4-dimensional vector, right? 9, -1, 1, and 3. At this point, all you have to do is subtract off the translational and rotational modes. So where do you find those? Most character tables, you could actually figure this out, right? Because we know how to derive character tables. You could figure out how an X vector translates a Z vector, an RZ vector, which is a rotation degree of freedom, RY, et cetera, how those transform. But you know, that's a lot of work and not really necessary, because most character tables and all the character tables that I give you on the exam, I'm going to give you the ones that are on Web Campus, have these functions listed, okay? And so all you have to do is look at, okay, where are X, Y, and Z? Well, X is B1, Y is B2, Z transforms as A1. So the translational modes, there's 3 of them, X, Y, and Z, and they're A1 plus B1 plus B2. Rotational modes are where our X, our Y, and our Z are. So that's A2, B1, and B2. And then you're just going to subtract them off. So I'm subtracting 3 A1s from 1 A1. That gives me 2 A1s. I had 1 A2 to start with, but I'm subtracting 1 off, so I don't have any left. And then I have 2 B1s that I started with, but I'm subtracting 2 off, so I don't have any left. And then I have 3 B2s, and I'm subtracting 2 off, so I have 1 left. So those are your normal modes for a water molecule, right? We have 2 A1s and 1 B2. So these are the fundamental symmetries of how bonds can contract and expand in a water molecule. And so there's 3 modes, and we can check this, right? We can check this using our 3n-6 rule, that there should always be 3n-6 normal modes for a nonlinear molecule. Water is bent, right? So it's not linear. And we have 3 atoms in water. So 3 times 3 minus 6 equals 3. And that's exactly what we got. We got 3 different normal modes. So what are those modes? It turns out that things that are A1 have to be totally symmetric. And we'll go into this later, how you can get, basically, how you can get these pictures, right? Just all from group theory and from knowing the symmetries. We'll do that later, towards the end. But for now, just see that, hey, look, we have, and sorry, this stretch for some reason is lagging with Zoom and everything running here, but the stretch is just, you know, going in and out. So, you know, the A1 is the totally symmetric representation, and the symmetric bend and the symmetric stretch look very symmetric. But the asymmetric stretch, right, has symmetry B2, and that's when one atom is going in, the other is going out. So it's going kind of like this, right? Okay, so that is great. And so we're going to stop here.